In topic 5, we covered translational kinetic energy. So this is the energy an object has as it moves forward or backwards. However, I tried very hard to write problems only where something was sliding, because rotational kinetic energy, so the energy an object has while it's rotating, is calculated using a different formula, which is 1/2 moment of inertia times the angular velocity squared. This means that the total kinetic energy that you would actually plug into your conservation of energy formula would be the translational plus the rotational. Now, if you have an object that's sliding, you just have translational kinetic energy. If you have an object that's just rotating, say you take your bicycle and turn it over and spin the wheel, that's just rotational motion. But if you ride your bicycle down the road, you are both moving forward, or the wheel is moving forward, and the wheel is also rotating, so you would have both translational and rotational kinetic energy. And it actually does make a difference. Dr. Baum and I were once testing a lab for Physics 111, very similar to what we do at conservation of energy, only we were trying not to do it with the air tracks. And so we had created a V and had a ball roll down the V. And when we calculated the energy, we got the results that we expected up to a point, where we saw that with altitude, potential energy increased, kinetic energy decreases, but when we plotted the total energy, it didn't quite go so right. It wasn't as horizontal as we expected it to be. So we put the equipment away, pondered it for a while, and eventually Dr. Baum realized that we had a ball rotating down a metal slot. So he went and measured the radius of the ball, calculated the rotational kinetic energy, and added that in, and all of a sudden our total energy was horizontal. So kinetic energy does matter when you're talking about something that is both rotating and moving forward. Otherwise, you're going to look like you're missing kinetic energy. Angular momentum is represented by the capital letter L and is equal to the moment of inertia times the angular velocity. Angular momentum is conserved when the net torque acting on the object is 0. When the system is changed. So we're not talking about collisions this time. What we're talking about often is a change in how the mass in the system is distributed. Because inside of the moment of inertia is both mass and radius. So you can change the moment of inertia by adding mass or removing mass from the system, or you can change the moment of inertia by changing the size of or radius of the object that is rotating. But in order for the momentum to be conserved, it has to be done without adding a torque to the system, which can often be difficult. So one example of this is an ice skater. So if you've ever watched figure skating, the ice skater will start with arms stretched out straight, spinning, and then as the ice skater wants to spin faster, the ice skater will pull arms in and start spinning faster. So the ice skater is effectively changing moment of inertia by reducing r with the same mass, making the moment of inertia smaller, and increasing angular velocity. All Alright, now you're going to get the opportunity to see Dr. Baum testing out the conservation of angular momentum.
What I have here is just a couple of 5 pound, excuse me, 2.3 kilogram masses. And I am going to, start myself turning, and then once again put myself up onto the stool so there are no external torques. And I'm going to hold these out like this, and then much like an ice skater or a ballerina, I'm going to slowly pull them in, and we'll see what happens. So first of all, I have to get myself turning, not too fast. You can have a lunch yet. It's actually pretty fast. So I'll go down a little bit. All right, ready? And I bring this in. And you notice I speed up. Slow down. Speed up. Slow down. Speed up. So the idea is that my angular momentum is supposed to be constant. With my arms short like this, as I have a very high moment of inertia, and therefore relatively low omega. As I bring them in like this, I goes down, because the rate of these masses goes down, and correspondingly omega has to go up.